All right, let's look at an example of how to compute the Fourier series for a periodic function that consists of impulses. So here I have kind of an impulse train. This type of signal becomes useful when we're looking at sampling of signals. All right, I'm not going to really talk too much about that, but let's say I've got this periodic function. I can see that it's periodic because it repeats. Looks like I have an impulse up, then one down by -2, then up by 1, down by -2, up by 1, down by -2. This guy's clearly periodic. So let's say what I want to do is I want to recreate, using the synthesis equation in MATLAB, I want to recreate an approximation to this function, all right, using the synthesis equation. And then I want to be able to do that, I first have to take this function, the true function x of t, and use this analysis equation here to be able to determine what the Fourier series coefficients are. Once I know those, I'll go into MATLAB and use the synthesis equation. Okay? So that I said in class there are 3 questions I need to ask myself to determine the Fourier series coefficients. These are the 3 questions, right? So what's the fundamental period t? What is the function x of t over 1 period, right? So I can plug it into this integral and then evaluate the integral. All right, so let's do that. All right, first is, what is the fundamental period t? Now, we define a period by basically saying, how much time does it take for the function to repeat itself? So in this case, I look at this and I say I've got an impulse up of height, impulse up here of area 1 at t equal to 0. And then at t equal to 2, it repeats. It's another impulse of area 1. At t equal to 4, it's another impulse of area 1. At t equal to 6, it's another impulse of area 1. So it looks like my period is t equal to 2 seconds. So omega naught is 2 pi over t, or pi radians per second. Okay. All right, so I've got my fundamental period. And then what I need to do is that I need to define x of t over 1 period. All right, so I'm going to define x of t over this first period here. So I'm going to say x of t, there's 2 impulses there. Now, the impulse, it looks like I have an impulse up at t equal to 0, an impulse down by 2 at t equal to 1. So what I'm going to write that is, it looks like I've got a delta of t, okay, minus 2 delta t minus 1, okay? Remember, the delta t minus 1 puts it at t equal to 1, because at t equal to 1, this guy becomes equal to 0, and I have delta of 0. So what that says is that t equal to 0, or sorry, t equal to 1, this whole function here is equivalent to the function delta of 0. Okay, so it has the same value that delta of t has at t equal to 0. All right, is what that's saying. Okay, all right, that's over 1 period. If I were to do it over the next period, right, and I wanted to integrate over the next period, I could have said that it was delta of t minus 2 times delta of t minus 3, okay, and so on and so forth. I'm going to choose to do it over this period here, all right, and evaluate it that way. So let's plug that in now when we evaluate the integral. So here's the integral, here's the analysis equation. Now one thing I'm going to point out is I just wrote down here a t at the bottom of this. That's a notation that we sometimes use when we say that we want to integrate over a period. So we're going to talk about the limits here in a second, but I'm just going to say I want to integrate over a period. It can be any period, all right? So if I write that integral, so I put 1 over t, so in this case that's 1 over 2, and again I'm going to say that I want to integrate over a period, and I'm going to plug in my x of t. So my x of t is delta of t minus 2 delta of t minus 1 times e to the negative j n omega naught t dt. All right. Now the question, let's get to what should the limits of the integration be. Let's just say you chose, for sake of argument, over one period beginning at 0 and going to 2. Okay? So if that was the case, that would begin right here and end right here. Now what's kind of ambiguous about that is that period now, if I defined it from 0 to 2, it's perfectly fine as a period, but what's weird here, because this impulse only exists at those locations, okay? Because it only exists exactly infinitesimally small at any location, this is a really weird integral to do. So we go back to sort of our definitions of the integral. So what we said about our definitions of the delta function. The delta function has an area 1. It is extremely high and extremely skinny. All right, so it's very, very high, very, very skinny. All right, essentially so skinny that it's infinitesimally small and infinitely large, so that its area is 1. Okay. Now, what we talked about is when I try to evaluate that integral, all right, by definition, what we said was the integral from negative infinity to infinity of delta of t is 1, okay? So what's tricky about this, guys, let's say you tried to do the integral from 0 to 1 of delta t. That we say is kind of ambiguous. Because everything sits at t equal to 0, having the limit of the integration being at the location where this guy exists is kind of ambiguous. I just want to avoid that altogether. Here in the notes, I talk about a way you could kind of think about that by saying, well, let's say I got really close to 0. But I don't want to be at 0. I want to avoid this. This is ambiguous. So what I'm going to do instead, all right, is I don't want to go from 0 to 2. I'd rather say, why don't I try going from negative 0.5 to 1.5. In other words, going from here to here. That's still a period of t equal to 2, but it avoids that ambiguity of saying that the impulse is located at one of the edges of the integration range. Okay? So that makes it a lot simpler. All right, so if we agree to do that, this becomes 1/2, let's break it up into 2 integrals. So from negative 0.5 to 1.5, delta t e to the negative j n omega naught t dt minus 2 times the integral negative 0.5 to 1.5 delta t minus 1 e to the negative j n omega naught t dt, like so. All right, now to be able to evaluate this, I have to go back and remember this thing we called the sifting property. Okay, so it looks like what I have in each of these integrals is some function f of t. Okay, where in this case the f of t is e to the negative j n omega naught t. And so what we said is if I take an integral, in this case negative 0.5 to 1.5 of delta of t times f of t dt. That's like saying what I'm going to do is, let's say f of t is some function that looks like this. Okay, and then I have the impulse here. It's like saying when I multiply the impulse by f of t, I just pick off the value of the function f of t at the point t equal to 0, and that's all I'm left with. In other words, this guy just becomes simply f of 0. Well, that's what's going to happen to this integral. Okay, And so the integral is going to get super simple. Now similarly, we'll do this. Here, right? Looks like that second integral is basically where I have f of t multiplied by delta t minus 1. That would simply be f of 1. Okay, so that's pretty convenient to be able to see that. So the sifting property, we call this the sifting property because what it's doing is it's sifting out the value of the function f of t. It's sifting that out from the main function at the location of the impulse. So you're sifting out one point from the overall function. Okay, so if I apply that to the integral that I was doing, so that's 1/2 times, in this case, so just to write it out, negative 0.5 to 1.5 delta of t. If my f of t is e to the negative j n omega naught t dt, all right, I'll come back and do the second half of the integral in a second. But that means that this guy just becomes whatever this e to the negative j n omega naught t is at t equal to 0. Well, that's simply 1, okay? So I see this guy becomes e to the negative j n omega naught times 0, or ultimately the number 1, okay? Let's fill in the rest of the integral. So I have minus 2 times integral 0.5 to 1.5 delta t minus 1 e to the negative j n omega naught t dt, like that. I'll evaluate that guy with the sifting property. Means that I'm going to need to evaluate that e to the negative j n omega naught t at t equal to 1. So I'm going to say minus 2 times e to the negative j n omega naught, like that. And just like that, my work here is done. I have determined my Fourier series coefficient. All right. Now, back at the beginning, I said, okay, well, if my goal is to try to approximate the function by evaluating this summation, then I can write a piece of MATLAB code to help me to evaluate x of t equal to this. Okay. Now, it's important to remember that if I sum from negative infinity to positive infinity, I get the true function. What I'm actually doing in MATLAB is I'm approximating it by saying, well, let's do capital N harmonics. All right? So I'm going to say going from n equal to minus n to n, where n can be any number. Let's start out with n equal to 100, right? So we're going to do alpha n e to the j n omega naught t, like that. Okay? So what my MATLAB code would do is I would say, well, I'd have a for loop that would say for each n, I would compute alpha n, then compute alpha n e to the j n omega naught t. This is just a number, remember? This is just one number. This here, however, is an array or vector, right? It's a series of numbers, right? It's basically over whatever time period I'm looking at, all right? I'm essentially going to get a function that covers that time span. And then basically I add this, I add alpha n e to the j n omega naught t to the rest of x. Okay, so the output of this will also be an array. Okay, so let's look at MATLAB code that will do that for us. Okay, so MATLAB Cobra I'm going to look at here is the first part here. So it's lines 1 through 20. So as I always should, I clear all. Let's give myself a little bit of, let's blow this guy up a little bit. All right, so I clear all. I put in the period, so t equals 2. I have omega naught, which is 2 pi over t. Then I define a time vector. Okay, and that time vector in this case, I have span for 4 periods. So from minus 2 times t to 2 times t. And then I create x, which is my ultimate output. So over here, x is my ultimate output. But I create it as this basically just a zero vector, a zero array. And then I have my for loop. All right, so notice in this case, I've set out with n equal to 100. All right, and what I've done is I've said, okay, alpha n, I went through and I calculated for myself what alpha n is. Again, remember that's just going to be a number. And then here I have alpha n times exponential j n omega naught t. That was what I defined as my step 2 over here. And then my step 3 is to take this function that I just, or this array that I just created, and add it to the broader x. Okay, so I'm going to highlight that, and I'm going to evaluate selection. All right, so there it is. All right, I can see this guy quite clearly. Let's compare. Remember, this is an approximation. The original function is this pulse train over here. Okay, so just verifying this guy for a second. I see that I have something going up, a spike going up at t equal to 0, a spike going down at t equal to 1, and then a spike going up at t equal to 2. This guy's clearly periodic with a period of 2. That was what we desired to have happen. One thing I notice about this is that if I look at the ideal function, it seems to imply that I have a height of 1 and then a height of minus 2. This guy looks like he's got a height of 100 and a height of minus 2. So the pulse downward is twice as big as the pulse upward, but it's 100 times bigger than what is shown here. This gets into kind of a fine point, right? If I go back to our definition of this impulse or delta function, what I said is that the delta function is really, really large, all right, near t equal to 0. So he's really, really high, right? Really, really high and really, really skinny, okay? And the true delta function has an area of 1, but he's super high and super skinny. So we said that the area is basically, in this case, epsilon times 1 over epsilon, where epsilon is getting super tiny. No matter how tiny it gets, that area is going to be 1. Okay, that's our definition of the delta function. So if I look at this guy, he's super high here. He's got a height of 100 and a height of minus 200. That's actually what we would expect. If I were to integrate over this area here close to this impulse, I would expect that area to be equal to 1. Okay? In other words, he must be super small. If I zoom in, go to my zoom, I see that he is pretty small. Okay, easiest way for me to measure that might be to put my data tip on here. I see that that's about negative 0.0148 on the x-axis, and that's about the same place, 0.015 on the x-axis. So that pulse there is pretty skinny and also pretty high. But one would think, though, that as I begin to approximate the real function, so if I include more harmonics, okay, I should get closer and closer to the real function. So in other words, if I look at this expression right here, if I let capital N be bigger, so I include more harmonics, I should get closer and closer to the true function. So based on that, what would I expect this pulse height to do as I included more harmonics? Right? What I would expect to have happen is that that pulse height would get higher and higher and higher, and the width of the pulse would get narrower and narrower. All right, so remember this guy, these two lobes right here, so this is negative 0.015, all right, ish, and this is 0.015-ish or 0.014, all right. Let's include 400 harmonics instead of 100, and let's see what happens to both the height and the width. Okay, so now I'll put in 400, and I'll do that again. And there he goes. So I can see that they got higher. So now it goes to 400 and minus 800. So I still have essentially the same behavior where I go up 1, down -2. But my heights have gotten higher. I expected my heights to get higher because I'm getting closer to approximating the real function. The thing to remember is when you look at the true idealized graph, we said we don't write the height on there. We write the area, okay? So in reality, these impulses are enormous, right? We can't really draw that in reality. So we denote it by this little arrow, and we write next to that arrow, not a height, but an area. So it's a little bit confusing. All right, so we said that because this guy got taller, he should also have gotten skinnier. Let's go to my zoom again, and let's zoom in here on t equal to 0. Zoom in again, he definitely got skinnier. All right, so let's take my data tip and look at the points here in this lobe. This is negative 0.0036, which means this guy should be at about 0.0036 as well. All right, way skinnier than what I had before. Before it was about 0.015. All right, so it's a lot skinnier than it was. It's a lot taller than it was. Okay. If I were to continue with that, I would see similar effects, right? He would get taller. So let's do 800 harmonics. I do 800 harmonics. Evaluate the selection. He gets taller still and skinnier. Without zooming in on that guy, you can kind of see that he's getting skinnier. And he's going down by, in this case, it would appear it's going up by 800 and down by negative 1600. So that 1 to 2 ratio that I see in the real plot is maintained. But what I see here has a dramatically different height than what I draw in this idealized picture. So just remember, the idealized picture, what we say is we draw an arrow, but we write the area under that pulse next to the arrow, right? It's not the height, it's the area. So in reality, what I have is something that's super big and super skinny, whose area is 1, okay? Now, one thing I do want to mention here with these pulses, as I draw this guy, I get these sort of lobes here, right? So basically what I see is artifacts of the fact that I'm making an approximation of the function using a bunch of harmonically related sines and cosines. Only if I included all infinitely many of the harmonics would these lobes here go away and I would get a true impulse. All right, so that's these sort of oscillations here are a little bit of an artifact of the fact that my approximation is imperfect. All right, so hopefully that example helps to understand how to approach some of the problems in your homework.